Hi, this is Eli Bell, and this is my discussion 13 video. It's on section 11.5, equations of lines and planes in space. And this is problem 39. So we're given two planes, and we need to determine whether the planes are parallel, orthogonal, or neither. So the first thing we're going to do is we're going to pull out the normal vectors. And we're just going to get those from the coefficients for the x, y, and z. So the first one is 1, 1, 1, and the second one, 2, negative 1, 1. Okay, and we can tell that these are not parallel because there is no scalar multiple that would make n1 equal to n2. So they're not parallel. And then we can check if they're orthogonal. And we do that with the dot product. So 1, 1, 1 makes this easy. So it's just going to be 2 minus 1 plus 1, which equals 2. And this is not 0. So this is not orthogonal. All right. So it's neither orthogonal or parallel. So this was A. Now we're going to do B. If the planes are neither parallel nor orthogonal, then find the measure of the angle between the planes. Express the answer in degrees, rounded to the nearest integer. Okay, so in order to do that, we have an equation, cosine pi equals the magnitude of the dot product between the normal vectors. Um, and that's over the product of the magnitude of the normal vectors. So we already have the dot product of the normal vectors. So let's get the magnitudes. All right, so this one's 1 squared plus 1 squared plus 1 squared, which is just radical 3. And second normal vector, 2 squared plus negative 1 squared plus 1 squared, 4, 5, 6. Okay. So from the first part, we already got that this one is equal to 2, the numerator, and then the denominator is going to be uh, 3, radical 3 and radical 6, which is just 18. And then I'm just going to enter that into the calculator. And we got 61.874, but a problem wants us to round to the nearest integer, so we'll call it 62. And that is part B, so now we can move on to part C. So it says, if the planes intersect, find the line of intersection of the planes, providing the parametric equation of this line. Okay, and we know that they're going to intersect because they are not parallel. So we're just going to start by letting z equal t. So for normal vector 1, we get x plus y plus, and then in subbing out the z, we get the t equals 0. And for our other one, again, subbing out the z for t. So I think it'd be simplest to solve the first one for y. So y equals minus t minus x. And then we're going to substitute that into this equation. So 2x, and then for the y, we're going to do minus t minus x plus t minus 7 equals 0. And now let's just simplify that. So 2x minus negative x, so 3x, and then we have t minus negative t, so 2t minus 7 equals 0. So we got 3x equals 7 minus 2t, bringing the t to the other side. And now we can just divide the 3. Cool, so we got one of them. Now we're going to go back to this equation up here on the left side, and we're going to sub back in what we just got for x. So, all right, just going to make the denominators match, and then distribute this negative. All right, so now I have minus 7 minus t over 3. And it looks like I've gotten my parametric equation of a line. I just got to write it down at the bottom. So x equals 7 minus 2t over 3. And then y equals negative 7 minus t over 3. And then z just equals t. And this is our parametric equation of a line. So that is problem 39. And just one last thing. We're just going to look at this graph that I prepared to show that everything works out. So these are our two planes, and you can see the line of intersection right there. And it's hard to tell from just one angle, but everything does check out. So that's it. Thank you for watching.